Okay, you've definitely seen the periodic table before, right? Hanging up on some classroom wall. And you might think of it as just, a boring chart of elements. But it is so much more than that. It's really a map. It's a guide to the fundamental building blocks of our entire universe.
And like any good map, it's packed with hidden patterns and clues. As you move across the table, you see that properties, like an atom's size or how reactive it is, they change in these really predictable ways. It's almost like the table is written in a secret language, a set of rules that governs all of matter. And our job is to learn how to read it.
So that's what we're going to do. We are going to crack that code. Why is the table shaped the way it is? What are these repeating patterns all about? And what deeper truth do they tell us about the nature of reality itself? To understand the code for the whole table, we have to zoom way, way in. We need to find a clue inside a single atom. And our search for that first clue begins, of all places, in the stars.
That's right. Almost every element you see here, the carbon in your body, the oxygen you're breathing right now, the silicon in your phone, it was all forged in the unbelievable heat and pressure inside stars and then blasted across the cosmos in giant supernova explosions.
So, how in the world do we know what's inside a star that's millions of light years away? I mean, we can't exactly go take a sample, but what we can do is analyze the next best thing. It's light. Light is the messenger, and it carries the secrets of the atom across the huge emptiness of space. And this exact same idea works right here on Earth. Just think about fireworks. That brilliant, fiery red color you see, that's strontium. That vibrant green, that's barium. Every single element, when you give it a little bit of energy, emits its own unique color of light. So what is actually happening down at the atomic level? Well, it is all about the electrons. When you heat up an atom, its electrons absorb that energy, and they get excited. They jump up to a higher energy level. But they can't stay up there. It's unstable, so they fall back down. And when they do, they release that extra energy as a tiny little packet of light, which we call a photon. And this is our first massive clue. The light that an element gives off isn't just a continuous rainbow. Nope. It's a series of very specific, very sharp, bright lines. It's like a unique barcode made of light. This is called an element's emission spectrum, and it is as unique as a fingerprint. So why these specific lines? Why not just a smear of color? It's because energy inside an atom is quantized. Think of it like a ladder. Electrons can't just hang out anywhere they want. They can only exist on specific energy levels, the rungs of the ladder. An electron can jump from rung 1 up to rung 3, but it can never, ever exist in between the rungs. This one idea is the key that unlocks the whole periodic table. Okay, so we've got our big clue. Electron energy comes in these discrete, quantized packets. Now, we need to figure out the rules of this weird ladder. What are the laws that tell electrons where they're actually allowed to be? It's actually surprisingly simple. You can think of it like an electron's address. First, you've got the main energy level, or shell. Think of this as the city the electron lives in. Then, within each level, you have sublevels, which we call S, P, D, and F. These are like the streets. And finally, on those streets, you have orbitals. These are the specific houses where an electron can be found. Now hold on, don't picture these houses as neat little paths, like planets orbiting the sun. It's not like that at all. An orbital is actually a region of probability. It's a fuzzy cloud that shows where the electron is most likely to be at any given moment. And these clouds have these really cool, distinct shapes. S orbitals are simple spheres, while P orbitals look kind of like dumbbells. And here is our last rule. It's called the Pauli exclusion principle, and it's beautifully simple. Each orbital, each one of those houses, can hold a maximum of 2 electrons. That's it. And if it has 2, they have to have opposite spins. You can just think of it as one pointing up and the other pointing down. And that's it. Those are all the rules we need. So now we have our rules. We know about the quantized energy levels, the sublevels, the orbital shapes, and that 2-electron limit. With just these few ideas, we can now build the entire periodic table from the ground up. We can finally crack the code. Okay, let's see how this works with an actual element, like lithium. It has 3 electrons, so where do they go? Following our rules, the first 2 electrons fill up that s orbital in the very first energy level. That level's now full, so the third electron has to go start a new level. It goes into the s orbital of the second energy level. We'd write its address out as 1s squared 2s1. And now, this is the moment where it all clicks. The periodic table's strange shape, it suddenly makes perfect sense. It's not random at all. It's a direct map of these electron orbitals being filled. The first two columns, that's the s block. The big block over on the right, that's the p block. The metals in the middle make up the d block. And those two lonely rows at the bottom, the f block. The code is cracked. The shape is the code.
So what does this tell us about how an element behaves? Well, pretty much everything comes down to the electrons in the outermost shell. We call these the valence electrons. They're the ones on the frontier, the ones that interact with the world and form chemical bonds. And here's the key. Elements in the same column all have the same number of valence electrons. That's why they all act so similar. It's why they're a chemical family.
All right, so now that we get the why behind the table structure, all those predictable patterns we talked about at the start are no longer mysterious rules you have to memorize. No, they're just the logical consequences of this beautiful quantum structure. Let's start with atomic size. As you go down a column, what are you doing? You're adding a whole new electron shell, a new energy level. So of course, the atoms get bigger. But what happens when you go across a row? You're staying in the same shell, but you're adding more and more protons to the nucleus. That stronger positive charge from the center pulls all the electrons in closer. So the atoms actually get smaller as you go from left to right. So when you look at the whole table, the trend is crystal clear. The biggest, puffiest atoms are down here in the bottom left corner, and the smallest, most compact ones are up in the top right. It's not a mystery anymore. It's just logic. And the other trends, they just follow right along. Take ionization energy. That's how much energy it takes to steal an electron from an atom. Well, for a big atom, its outer electrons are super far from the nucleus and aren't held very tightly. They're easy to pluck off. For a small atom, though, those electrons are held really tight, so it takes way more energy. So the trend for ionization energy is the exact opposite of the size trend. And it's the same story for electronegativity, which is basically how good an atom is at attracting electrons in a bond. Small atoms with a really strong nuclear charge, like fluorine up here in the top right, are the absolute best at it. They're like the bullies of the playground, just grabbing electrons. It all comes back to size and charge. So you see, when you put it all together, there's this incredible logic to it. Atomic size, ionization energy, electronegativity, none of these trends are random factoids to memorize. They are all the direct, visible result of those simple, elegant quantum rules that tell an electron where it's allowed to be. And that kind of leaves us with one final, pretty big thought. From the fiery heart of the most distant star to the atoms that make up you and me, everything is built according to these same few quantum rules. The entire universe, in all its mind-boggling complexity, seems to be playing by a surprisingly simple and elegant set of laws. And what does that say about the fundamental nature of reality itself? Well, that's something I think about.